Today I will be talking about nuclei, the chapter nuclei for class 12. Here it starts from the Rutherford experiment. A Rutherford experiment he performed an experiment in which alpha particles were scattered on a gold foil, and he did the calculations on the basis of Coulomb's forces. So what happened that if an alpha particle of 5.5 mega electron volt strikes a nucleus of a gold foil, that means it can't strike it, but it remains at a distance of 4 into 10 to the power of minus 14 meter. That means a alpha particle of 5.5 mega electron volt of this energy, its nearest approach to the nucleus of a gold foil is 4 into 10 to the power of minus 14 meter, and the size of the nucleus must be smaller than this value. Now again, if alpha particle of energy more than 5.5 mega electron volts were bombarded on the gold foil, the distance of closest approach was less than that of 4 into 10 to the power of minus 14 meter. So this may be due to this deviations may be due to the nuclear forces, but Rutherford he calculated on the basis of Coulomb's forces. So here the perfect size of the nucleus was unavailable. So now instead of alpha particles, electrons of different size of nucleus were bombarded on the gold foil, and the result, it was found that the size of the nucleus is proportional to the cube root of mass number. That means size of the nucleus, that is R, is proportional to the mass number, that is A to the power of cube root, that is A to the power of 1 by 3. And this R is equal to R naught A to the power of 1 by 3, and the value of R naught was some 1.2 into 10 to the power of minus 15 meter. So they were able to find the size of the nucleus by the help of this formula, that is size of the nucleus is proportional to the cube root of atomic mass. Now earlier, that is mass conservations, energy conservations, they were separate, but the Einstein E is equal to mc square showed the interrelation between energy and mass. That is, mass is nothing but, after all, it is an energy. So here comes one thing. They considered the example of, in this book, they have considered the example of oxygen. Its atomic mass is 16. So number of proton is 8 and number of neutron is 8. When they calculated the mass of the oxygen, and the mass of the oxygen calculated experimentally by a spectroscopy experiment, it was found that the actual mass was less than the calculated mass of the nucleus of oxygen atom. So difference in this mass difference in this mass was called the mass defect. And this mass defect, according to the Einstein formula, E is equal to mc square, is interconvertible. So this is the energy. So this is the energy which is the binding energy which binds the nucleons of a oxygen atom. This is the binding energy which binds the nucleon of the oxygen atom. From here we get three types of results. Binding energy, that means binding energy, that means this much of energy must be applied externally to break the nucleus of oxygen atom, but it is impossible to break the nucleus of an oxygen atom. And at the same time, the another result which comes out, that this much energy is released when an oxygen nucleus is formed. So here comes the binding energy. That means this is the energy with which the nucleons are held together. Now it was found that the atomic mass greater than 30 and less than 170, their binding energy was almost constant. Here they made one thing, that instead of binding energy, they did a little bit of improvement, that is binding energy per nucleon, that is equal to binding energy divided by the mass number. So here, when a graph was plotted between the binding energy per nucleon and the mass number, it was found that the mass number greater than 30 and less than 170, in this range the binding energy was practically constant, and it was around 8.5 mega electron volt. And the atomic mass greater than 170, which are heavier nuclei, here the binding energy was less, and light nuclei, that is less than 30, here also the binding energy per nucleon was less. Now here comes some of the conclusions. That means binding energy, the nuclear forces which are responsible for the binding energy, and these nuclear forces are of short range. So here what they want to tell us, that within this range, within this nuclear force range, all the neighboring nucleons, they are held together by the binding energy. So this binding energy was proportional to the number of nucleons in the neighborhood of the nuclear forces. Any nucleon which was outside the nuclear forces, they do not contribute to the binding energy. So here what happens, two things comes forward, that if a mass number greater than 170, if it transforms into nuclei of greater binding energy, that means greater binding energy, that means the mass number must shift between 30 and 170, so it will release energy. So such release energy is called as fission process. And another result which came forward, if we take mass numbers less than 30, lighter nuclei, if we take lighter nuclei and they combine to form a heavy nuclei whose binding energy is high, that means it again falls within the range 30 to 70. So binding energy is high, that means it will release energy, and this is called the fusion process. FUSION, fusion, and the early was fission, FISSION. So in two ways energy are released. The first is that a heavier nuclei that is greater than 170, if they transform into a nuclei whose binding energy is high, that means it has come within the range of 30 and 70, then it will release energy, and this is the fission process. And if two light nuclei that is below 30, if they combine to form a heavy nuclei whose binding energy is high, that means again they falls in between 30 and 70, it will release energy, and this process is the fusion process. So in these two ways energy are released, which we get conclusion from the binding energy. So here we find that the nuclear forces are short range, remember, and if you move further away, then your nuclear forces will decrease and it will come to zero. So these nuclear forces, they are more stronger than the Coulomb's forces and the gravitational force, but they are short range. If we move beyond this nuclear force, then your nuclear force gradually decreases to zero, and here comes the Coulomb's forces comes into existence. So from this process we come to know that energy is released in two ways. Now we come to radioactive activity. So radioactivity, here there are two processes. One is the fission process and another is the fusion process. What happens in fission process, that is uranium, whose atomic mass is 235, when it is bombarded with a neutron, it becomes 236 atom mass, that is mass number becomes 236, and it splits into barium and krypton. It splits into barium and krypton and releases energy, plus 3 neutrons are also released. So this is a chain reaction, and in this way a huge amount of energy is released, because here you see that the atomic mass of barium and krypton, that is 144 and 89, which falls in the range of 30 and 170, they have high binding energy, so they release energy. So such process is the fission process. But next is the fusion process. In fusion process we find that two light nuclei, they combine to form a heavy nuclei whose binding energy is higher, so it will release energy. Now here comes the main point, that is, in case of two protons, they have an energy barrier. Two protons, they have an energy barrier, and we have to cross that energy barrier. So the two protons, they have an energy barrier, and we have to cross that energy barrier. To cross that energy barrier we require heat energy. That means a temperature of round about 3 into 10 to the power of a high energy temperature is required. 3 into 10 to the power of most probably 8 Kelvin. 3 into 10 to the power of 8 Kelvin. I do not remember particularly clearly. but in fusion process it is almost like this, that is 3 into a high temperature is required. So fusion process, it takes place in the sun. So here the sun is internal, there is a huge amount of heat energy. So this heat energy can overcome the energy barrier, and the two hydrogen atoms, they combine. First they combine to form deuteron, then these two deuterons combine to form helium of lighter mass number, that is 3, and then this 3 mass number 3 helium atom combines to form heavier helium atom, that is mass number 4, and releases a huge amount of energy. So in the sun, that high temperature is originally present in it, so it can overcome the barrier between the two hydrogen atom, and they combine to form a heavier nuclei, and a huge amount of energy is released. Now here comes an important conclusion of nuclear forces. The important conclusion of nuclear forces is that the nuclear forces between neutron-neutron, proton-neutron, proton-proton is approximately, it is the same. It is approximately, it is the same. So this is all about your nuclei given in the chapter nuclear.